Well, good day and good day to you. Welcome to MV Tutors. My name is Figa Manana, and today we are doing the topic of acids and bases. Okay, so acids and bases. Okay, so these are the types of questions that we want to be able to answer at the end of the session, and indeed you should be able to answer it because after the theory and learning the principles to answering these questions, we are actually going to answer this particular question. So if this is something you are interested in, then stick around and we will help you. I will help you. Okay, so let's get right into it. Okay, so let us start with the definitions because it's very important to understand the definition of the terms. So let's start with an acid. We'll define an acid and then we'll define a base as well. And the definitions will be according to Bronsted Bronsted Lowry. We'll start with the Bronsted. There's basically two definitions that are used, but we'll start with this one and then we'll do the other one later. So, according to Bronsted and Lowry, an acid is just basically a proton donor. Okay, it donates a proton, and the proton we're talking about here is a hydrogen ion or just an H. Let's call it an H for simplicity. Okay, and then a base is a proton acceptor, that which accepts a proton, which is still the hydrogen ion. That is what is called an acid. So let's do a quick example. Let's say we have HCl plus, let's add water into it, H2O. That will give us H3O plus Cl. Okay, so let's just look at these two. Okay, so if you look at these two, one donated a hydrogen ion to the other and H to another. Okay, so how can we look at this? So yeah, H2O became H3O, which means it gained an H, and then HCl became Cl, which means it lost an H or a hydrogen. So we can clearly see that this H over here was donated to that H2O. So, which means that HCl is the donor, and then this H2O is the acceptor, right? So, because HCl is the donor, that means that HCl is the acid, okay? And H2O then is the acceptor, so it becomes the base. Okay, so just like that. While we are on these definitions of donating and accepting, I want us to do this topic called conjugate pairs. Let's get right into conjugate pairs. Okay, so there's basically two things that I want you to accept, or I want you to learn about conjugate pairs. First of all, we must know that a conjugate pair is a pair of acid, and it's always paired with a base. So this is on one side, the reaction side, and this is on the other side, the product side, or it can be product side and reaction side, depending. And also what I want you to use here is the Bronsted-Lowry theory, that the difference is just an H. Okay, so let's say difference, conjugate pairs have a difference of hydronium ions. Okay, all right, so let's quickly look at an example. Let's say now we have NH3 plus H2O. Okay, and that is going to give us NH4 plus OH. Okay, so let's look at this. So first of all, we said it's a pair of an acid and a base. Okay, so that's what we're looking for, an acid paired with its base, and they should have a difference of H between them. Now if you look at NH3, it definitely has to be paired with NH4 because they look similar. Okay, and the difference between these two is just an H. This N has 3 H's, this N has 4 H's. Okay, and then the other pair is H2O and OH. This O has 2 H's, this O has 1 H, so these are pairs. The difference between them is an H. Now remember, we said that an acid, to identify which one is an acid and which one is a base, we do this very same exercise again. If H2O became OH, that means it lost an H, and NH3 becomes NH4, it means it gained an H. So this H over here was donated over there. Okay, so H2O is the donor, and then NH3 is the acceptor. Okay, so if H2O is a donor, then H2O then is the acid. If NH3 is the acceptor, then it is the base. Now coming back here to the actual pairs, then starting with the acid. Okay, let's start with H2O because that's the obvious one from this side. So H2O is the acid, and then OH, its pair, is the base. With these ones, if this is a base, then NH3 must be the acid, so it's NH4 must be the acid, and then its conjugate is NH3. Okay, well, there's something I want you to notice over here between the acids and the bases. Okay, if you look at the acids between the pairs, the acids always have one more H than the other. So if you look here, this O has 2 H's, this O has 1 H, so this is the acid. Okay, and this is the base. If you look at these ones, this N has 4 H's, this N has 3 H's, so that's the acid, that's the base. So the acid always has more hydronium ions than its conjugate base. Okay, so basically that's what I want us to look at. Even here, this first one that we did here, okay, so the conjugate pairs here, HCl and Cl. So starting with the acid is the one that has more H's, so the pairs here would be HCl, and Cl has more H, and the other pair, this is this one, so we'll start with H3O, it has more, and then H2O. Okay, so acids this side and bases this side. You can see these ones, the acids always have one more H than the other between the conjugate pairs. Okay, now let's go into the other definition. Okay, so let's look at the definition according to a man called Arrhenius. He defines an acid as well and a base. So according to him, he says that an acid is a substance that ionizes to produce hydronium ions or H3O. Same thing between these one. A base, you can say it dissociates as well, but can also say ionize. It's basically the same thing, but let's say it dissociates. It dissociates to produce a OH, hydroxide ions. Okay, and both of these happen during hydrolysis. Okay, both of these happen during hydrolysis, which means the addition of water. When you add water to an acid, it will always produce H3O. When you add water to a base, it will always produce OH. So whatever produces H3O is an acid. Whatever substance produces OH when under hydrolysis is considered a base. Okay, let's look at an example. So if we remember we had HCl and we add water in it and it produced H3O. So because plus Cl, because it produced H3O, that means HCl is an acid because it produced H3O. Okay, now let's look at another one. Sodium hydroxide, let's add water to it, H2O, and it produces an A plus OH, so it dissociated. Now because sodium hydroxide produced an OH, okay, that means it must be a base. Under hydrolysis, when you add water to it, it dissociated to that. So that's it. Now also, if you were to look at our previous examples, this one here, okay, remember we added water to it and it produced OH, so it must be a base because it produced OH. While this one produced H3O, so it must be an acid. Okay, so two ways of identifying an acid or a base. That's it. Okay, so I now want us to talk about something called an ampholyte. Okay, an ampholyte. What is an ampholyte? So basically, an ampholyte is a substance. It's a substance that can act as an acid in one scenario and also a base in another scenario. That means it can donate, or it can accept an H ion or a hydronium. Okay, it can donate or accept a proton, which is a hydronium. All right, now examples of these, for example, water is one of them, and we also have HSO4. These are the common ones now. HPO4 and then H2PO4. But let's take a look at them in action. Okay, let's just see an example. So if you take say one of them, let's take HSO4, and then I add a hydronium, and then it becomes H2SO4. So what happened? Okay, this H here was donated over here so that it becomes H2SO4. So this is the donor, so this must be the acid because it donated, and then this is the acceptor, so this then must be the base. Okay, so you can clearly see HSO4 is a base in this instance. Now let's look at another reaction where you take HSO4 and it dissociates, or it just becomes H plus SO4. So what happened here? You can clearly see that this H was donated, okay, because this HSO4 became SO4. So then that means since it donated, it must be the acid. Okay, so that is an ampholyte. Okay, let's talk more about acids and bases. Okay, so we've got acid and bases. Now, what happens when you add an acid and a base? So an acid and a base reaction. That's what I want us to talk about shortly. So what happens is that when you add, when you say an acid and then you add a base to it, okay, you always get a salt and water. Okay, let's take an example. Strong acid, very strong acid, we're going to use HCl, and then you add it to a very strong base, which is sodium hydroxide. You're going to get a salt plus water. Okay, so let's start with the water here. The water we know is H2O. So I've taken this H here from the HCl, and then I've taken the OH from the sodium hydroxide, so I'm left with sodium and chloride. This then, sodium chloride, is the salt. Well, if you know these things, then you will know that actually sodium chloride is table salt. Okay, it's your table salt. Okay, let's now talk about titration. Okay, what is titration between acids and bases? So an acid base titration Okay, what is that? Well, what does it do? It determines, for example, it determines the concentration. It determines the concentration of an acid by neutralizing it. Okay, so it neutralizes it, neutralizing the acid with a base of, so you know, of known concentration. Okay, so it's not just about an acid, but also you neutralize a base. You neutralize a base using a acid. Okay, let me just draw it out for you. So you have say we have a container like that, and it's filled with let's say a base. There's a base in here, so you will titrate it with an acid. Okay, you titrate it with an acid until it's neutralized. Okay, until it's neutralized. So basically that's what titration is in basic terms. So you'll take this until it's neutralized, okay, and add acid, and vice versa as well. You take a base, okay, or you take a base, you neutralize the acid. Okay, so it's filled with acid, you drop base until the acid is neutralized. That is what is called titration of an acid and base. So all titration does is neutralize it, and that way you can determine the concentration of one using the other. Well, I just want to bring your attention as well, while we are here, to the basic formula that says a concentration is really number of moles over a volume. Okay, so also if you make n the subject of the formula, you get concentration, and volume you get n. So there is a formula where you can take the concentration of an acid and the volume of an acid is equals to the number of moles of an acid divided by the concentration of the base times the volume of the base, equals to the number of moles of acid over the number of moles of a base. Okay, so now this is where, just to define the terms, C stands for concentration, concentration, and then V is just the volume, and then N is just the number of moles. Now this formula is in your formula sheet. If they ask you a simple question about it to solve that, then you can basically use it. Okay, it's just one of the principles that are required to solve questions You don't need to cram it, but I just wanted to show you where it comes from. Okay, then that's it. Okay, so I want us now to talk about pH. Like, what is a pH? Well, all the pH does really is just to determine, okay, the degree of acidity, okay, or basicity, okay, or basicity of a solution. Okay, so the other thing that you must know about this is the definition of pH, or rather the formula of a pH, how to solve it. Okay, so pH is always equals to the negative log of your hydronium ion, okay, which is basically the same thing as saying the negative log, this is still hydronium, H3O. It's the same thing, same thing. Okay, so I also want to bring your attention to this, is that if your pH is less than 7, then less than 7, it's an acid. Okay, if the pH is equal to 7, then it's just, the solution is just neutral. It's neither acidic or basic. Then the last one, if your pH is more than 7, then it's a base. That's it. Okay, so this is just talking about the different pHs. Now I also want to name but a few. Okay, should I name them now or define a pOH? Let's start with a pOH. Okay, so if a pH is the negative log of that, then there's something we call the P, because remember, this has to do with the acid. Now this has to do with the base. If you have a base in your definitions, in your solution, but you want the pH of the solution, you can still solve it, or you can also solve a pOH. So a pOH is basically the negative log of the concentration of your hydroxide. Okay, so you see, remember, an acid produces a hydronium and a base produces an OH. Okay, but added to that, there is a formula that says pH plus your pOH. Okay, if you add them, they equal 14. So for example, if you have a pOH, you're giving a pOH and you want to solve a pH, you just take this to the other side, subtract it from 14, you get your pH basically. Okay, so now I just want us to talk a little bit about strong acids and strong bases. Okay, so what is a strong acid or a strong base? So let's just start with a strong acid. So a strong acid is something, it is an acid that ionizes completely. So all of it ionizes, it dissolves, it ionizes completely. Okay, it ionizes completely. Also, another property of a strong base is that it has a high conductivity. It's highly conductive. Okay, so examples of these a strong base. I'm just gonna give you three of them that we know. Number one is hydrochloric acid. It's like the strongest. Hydrochloric acid. So it's HCl, and then number two, okay, we have sulfuric acid, sulfuric acid, and that one is H2SO4. And then the third one I'm giving you is just nitric acid. These are strong. You must know about them. Nitric acid is it's HNO4. Okay, so if strong acids ionize completely, then strong bases then also, well, ionize completely, but we are using the word dissociate. Okay, so they dissociate completely. Okay, and then examples of these, just giving you three of them that you must know about, is sodium hydroxide, okay, which is NaOH. So we've got sodium hydroxide. Two, we have potassium hydroxide. Potassium, double S, hydroxide. Okay, and potassium is KOH. And then third and final one, I'll give you barium hydroxide. So you see all the actually all the strong bases have a they have an OH in them. Okay, so if you look at your what do you call this, your periodic table, all of these are on the first column, and then barium is on the second column. So that's why we have a 2 there, and we'll have a 1 there. Well, we don't put it, but we have a 2 there. Well, that's another lesson for another day, but let's just keep it this way. Hydronium hydroxide is written like this. Okay, so these are, what does it mean then if these are strong? Why do we need to know these? Well, the reason we need to know these strong ones is because basically the concentration of a strong acid is always going to be equal to the concentration of its hydronium ion, or it, well, let's just bring it down a bit. What did I do? Okay, let's bring it back to where we were. Let's bring it back to 100%. That's what we want. Okay, right there. Okay, so that is H3O. Okay, all right, so this will be very important in calculation. Also, sodium hydroxide is for a strong basis. Okay, the concentration of sodium hydroxide is always going to be equals to the concentration of a hydroxide. That's why it's strong, because it dissociates completely, so it's always gonna be 1:1. But so on top of that, I wanna just talk to you about this thing, the difference between a monoprotic acid and a diprotic acid. So a monoprotic acid is, well, mono means one. Okay, so it has one H, so it's monoprotic. It's a monoprotic acid. It has one H. Okay, so in a monoprotic acid, and 1 mole, you have the ratio 1 mole of a monoprotic acid is also 1 mole of the hydronium, let me say H plus. Okay, so an example of a monoprotic acid is this one, HCl. Okay, so it's monoprotic. Now a diprotic acid, 1 mole of a diprotic acid equals to 2 moles of your hydronium. Okay, how do you spot a diprotic? It has 2 H's. So an example is this one. So we have H2SO4. Okay, so now that becomes diprotic. There's also, 3, if it has 3 H's, then it's 1:3, 1:2. Okay, so why do we need to know this? Because when we come back to sulfuric acid, the concentration of sulfuric acid is equals to, because it's diprotic, so it's 2 times the concentration of your hydronium. This is also important when calculating this one here, nitric acid, the concentration of nitric acid. Now you need to know, is it monoprotic or diprotic? It's monoprotic because there's one H, so hydronium ion is just 1:1. Okay, because there's one H, 2 H's there, 2 H's. Basically, it's like you're balancing the H's, 1:1. Okay, you got 2 there, so you must have 2 H's there, and these are concentrations, so remember that. Okay, I think now we basically have all the tools that we need to answer the question that was given in the beginning. These are the principles that you need to know in acids and bases in grade 12. Well, let's get into the question now and see how we can do that. Okay, so here we are at the question again. We'll go through it real quickly because we are running out of time. So it says ammonium chloride crystals, there they are, dissolve in water to form ammonium and chloride ions. the ammonium ions react with water according to the balance equation below. So there you take the ammonium and then you add water to it and it becomes ammonia and hydronium ion. Now it says question 7.1.1, let's do it right this side. Write down the name of the process described by the underlined sentence. Ammonium ions react with water. Well, we spoke about this in the beginning. When you add water, we call it hydrolysis. Well, it's hydrolysis, hydrolysis. Well, it's up to you how you pronounce that. As long as you get the spelling right, we are good. And then 7.1.2 then. Oh, that's too thick. Okay, let's bring it down a bit. Okay, so 7.1.2 is ammonium chloride acidic or basic in the aqueous solution? Give a reason for your answer. Well, basically we need to see which one donates to who, which one loses an H, because the one that loses an H between these two is the acid, then the other is a base. So let's look at this. NH4 becomes NH3, but H2O becomes H3O. So basically it's like we took one H from here and you donated it to there so that it becomes H3O. So because this is the donor, that means the ammonium chloride is acidic. Okay, you can use either definition. Okay, based on donating, it's acidic. So they said give a reason. You can say because it donated a hydronium, or just say an H plus ion. Or using the other definition, you can say it formed H3O. When you added water during hydrolysis, it formed H3O. So because it formed H3O, that means it's an acid. Okay, so it formed H3O ions. Okay, so you can use either reason. Both of them are correct. This one is Arrhenius. I mean, a proton donor is Arrhenius. I mean, Brosted and Lori is a proton donor. Arrhenius is the other one. It forms a H3O ion when during hydrolysis. Okay, let's move on. 7.2. Let's go to 7.2 now. Let's make sure our pen is small. So, oh, it's still big. Let's make it small. I want it small. There. Let's see. 7.2. Okay, a certain fertilizer consists of 92% ammonium chloride. A sample of mass X grams of this fertilizer is dissolved in 100 centimeter cubes of 0.1 mole per decimeter cubed of sodium hydroxide solution. Okay, sodium hydroxide solution is given by that formula. The sodium hydroxide is in excess. So what I want us to do here is actually let's draw out what's happening so that we can better understand the question. So it looks like we have a box of fertilizer. Okay, this is a fertilizer, and the fertilizer has it has this is fertilizer, right? It has 92% ammonium chloride. So ammonium chloride is this, and I should have made my box a little bit bigger so that I can write on it. Okay, let's go back and write. 92% of it is NH4Cl. Okay, so that's our box of fertilizer. Okay, so what's happening now? A sample of mass X of the fertilizer is dissolved in 100%. Okay, now we now have a container, and it has 100 centimeter cubed volume. Okay, it's dissolved 100 of sodium hydroxide. So this is sodium hydroxide, NaOH. Okay, and it's a liquid, right? Cool. All right, so this is our container, right? Okay, so what else can we get? Of 0.1 concentration of it. So we have the concentration of concentration, which is 0.10 mole per decimeter cubed. So there's a difference between these two. All right, so now we understand what's happening. Okay, so we have two different things. That's fertilizer and that's sodium hydroxide. So what's happening is that you're taking the fertilizer, you are actually putting parts of it inside this 100. And what we've been told is that well, yeah, that's what's happening. Now they say calculate the number of moles of sodium hydroxide in which the sample is dissolved. Okay, so what do we know about number of moles? We know that the number of moles is actually equals to the concentration times the volume. Okay, so what is the concentration? And we are talking about sodium hydroxide here, right? What's the concentration of we've been given 0.1, that's the concentration, times the volume. We've been given 100 centimeter cube, but we need to convert it to decimeter cube. So conversion is dividing by 1,000. So if we divide by 1,000, that's where we get our conversion. So we're just gonna put this in a calculator real quickly. Okay, this is the calculator that you should be using. So it's 0.1 times 100 divided by 1,000, just like that, and then we get, okay, it's converted to a decimal. We got 0.8, what was it? 0.01. Okay, mole. That's it. Okay, so it says during a titration, 25 centimeter cube of excess sodium hydroxide solution is titrated with 0.11 mole per decimeter cubed of hydrochloric acid solution. So remember that the sodium hydroxide is a base, so you titrate it with what? An acid. So basically we have a flask here. We have a flask and it's filled with 25 centimeter cubed 25 centimeter cubed of what? Of the sodium hydroxide, and it is titrated with this. So the titration is happening here. So it's titrated with hydrochloric acid. And what do we know about the hydrochloric acid? Is that it has a concentration of 0.11 mole per decimeter cube. Okay, so you're taking drops of it and you're putting it inside here, and there must be some sort of indicator that will change color once it's neutralized. Okay, so but let's read on. I just wanted to write what we've been given so that we can better visualize it. Now at the end point, it is found that 14.55 centimeter cube of hydrochloric acid was used to neutralize the sodium hydroxide solution according to the following balanced equation. So then we used a volume, just to continue with that. We used a volume of 14.55 centimeter cubed of HCl to neutralize this 25 centimeter excess sodium hydroxide. So it's like they took 25% of this 100%. Okay, out of this 100 they took 25 to titrate it. Okay, so now let's read the question. Calculate the mass X in grams of the fertilizer sample used. Okay, so we need to be able to take what is happening at the end so that we can solve what is happening at the beginning. So what do they want? They want the mass. So now to calculate mass, we know that number of moles is mass over molar mass. So mass is really number of moles times the molar mass. And what do they wanted of the fertilizer sample? Okay, so then the fertilizer sample includes is the NH4Cl. So the fertilizer is 92% of that. So the fertilizer is 92% of this ammonium chloride. Okay, so this is the end goal. So now it means we need to solve the number of moles, okay, and then solve the molar mass. Okay, so let us start with the hardest one. Well, basically, let's start with the easiest one, which is actually the number of moles. Now you need to check your periodic table, but the molar mass is going to be N plus H times 4, not 3, because we got 4 of them here. What happened here? It's N plus H times 3 plus chloride. Okay, now if you check your periodic table, you will find that N has a value of about 14, H has a value of 1, times 4. Oh, sorry, that's what I meant to change there. Okay, It's supposed to be a 4 because there's 4 of them, plus Cl. You'll find that Cl is about 35. So if I add these up, okay, let's bring my calculator once again. We're gonna have 14 plus 1 times 4 plus 35. Okay, and that gives us about 53. Cool, so we have the molar mass. We're good with that. Now we need to solve the number of moles. So that's where things get a little bit dicey. Okay, so let's start here. Let's start here at the end here. So at the end there, what we have is that we have this formula, okay, HCl plus NaOH. Okay, so we have information on HCl, and then we can find the number of moles because we can see it's 1:1, so we'll find the ratio there. So let's start there. So the number of moles, we're talking about HCl now because we have information, is going to be equals to, if you remember the formula, that includes concentration and volume. So the concentration will be 0.11, because you can see it over there, times a volume of 14.55, and this volume is given in centimeter cube. So in order to convert it, we need to divide by 1,000. Okay, so let's see what that gives us. Let's bring our calculator. So we have 0.11, not 0.11 times 14.55 divided by 1,000. That gives us, I don't like it in this form, but anyway, it's more accurate. What was it? It's 1.6 times 10 to the power 3. I'll leave it at that. Times 10 to the power minus 3. Cool. So these are the number of moles of HCl. Now this means based on this, we can, because it's 1:1, the number of moles then of sodium hydroxide is also equals to 1.6 times 10 to the minus 3, because the ratio between the two is 1:1. All right, but remember this is actually in the 25 volume, a volume of 25 centimeter cube. But now we need to take this information from the 25 and be able to apply it to the 100. Okay, to the 100 centimeter. We're working backwards so that we can reach actually the mass of the sample. So now we've taken all the information from the 25. Let's apply it to the 100. How are we going to do that? Well, we know that in the 25, okay, oh, that's too much zooming. I want it to zoom out a bit. Okay, so we know that in the 25, okay, in the 25 centimeter cubed, we have 1.6 times 10 to the power minus 3 that's the volume, and then this is the concentration, or rather not the concentration, the number of moles of sodium hydroxide. But in the 100 now centimeter cubed, that's what we need to solve. Okay, so then x is just simply gonna be, we're gonna cross multiply, and then we're gonna get 1.6 times 10 to the power minus 3. All right, and it's gonna be times 100 divided by 25. Okay, which is cross multiplied, right? Cool. Let's put that in a calculator real quick. So if we bring it this side, then we have that times 100 divided by 25, and we get 6.4. Okay, cool. So we get x is 6.4 times 10 to the power minus 3 mole. Now this is in the 100 centimeter cubed volume package. So that's the number of moles that are in the, if you convert from 25, you upscale it to 100. But now this is what we must know about a number of moles. I always say that the initial number of moles is equals to the number of moles that are used plus those that are in excess. Okay, now we've been told that the excess was these ones in 25. Okay, so, and we are interested in the used ones because the question says calculate the mass of the fertilizer sample used. So it's very specific to say used. So we want the used ones. If it said in excess, then we could have calculated that. Initial, we calculated it initially. Okay, so initially here we calculated it 0.01 over there is equals to the used ones plus the ones that are in excess are these ones that we just calculated, because remember we use the excess information of the excess one because they told us that it was in excess over there, remember? So this is the excess one, and then when we upscaled it, it was 6.4 times 10 to the power minus 3 there. So in order for us then to actually solve the used ones, we can say then the used number of moles is equals to 0.01 minus 6.4 times 10 to the power minus 3. Okay, let's bring back our calculator. Just gonna do it old-fashioned way. Minus 6.4 times 10 to the power negative 3, just like that, old-fashioned way. Oh no, it's not 1, it's 0.0, it's 0.01 minus that, and then I get 8.6. 8.6, let me just look at it. Was it 8.6? Oh no, 3.6. My bad. I had something blocking me on my screen here. It's actually 3.6. times 10 to the power, let's check it again, minus 3 to the power minus 3. Oh, sorry, I just remembered that you can't see my calculator. I've been bringing it up, but you guys haven't been seeing. I'll correct it next time. But anyway, we get 3.6 times 10 to the power minus 3 mole. Okay, so let's think about this clearly. This is mole of what? This is mole of sodium hydroxide. Okay, but now if you look at this, what we are interested in, we've found hydroxide. We are interested in the ammonium chloride, right? So that we can use the ammonium chloride to calculate the number of moles of the fertilizer. Okay, so fortunately for us, we can see that based on the formula, it's also 1:1 over there. So the number of moles of sodium is equals to the number of moles of the ammonia chloride. Okay, so then we can then say between sodium, ammonium chloride and sodium hydroxide, it's also basically 1:1. So that means 3.6 times 10 moles of sodium chloride. They also, it gives you the same. You also get 3.6 times 10 to the minus 3. So this is the number of moles that we have used. So now we can use these number of moles to calculate now the mass of it. Okay, so we have the number of moles and then we have the molar mass. Okay, so we have both variables that we needed. Remember, we said the mass is equals to the number of moles times the molar mass, the number of moles times the molar mass. So number of moles, we have it as 3.6 times 10 to the power minus 3 times the molar mass, we found it to be 53. Okay, so we put that in a calculator, and then let me just put it in a calculator. Even though you can't see this, you know, it really sucks that you can't see it. I wish you could. So it's times 53 and I get 0.19 grams. Okay, now this last part is very critical. This is 0.19 grams of what? Of the ammonium. It's of the ammonia chloride. Okay, but we've been told that this fertilizer contains 92% of ammonium chloride. Okay, the whole fertilizer is not just made of ammonium chloride. So finally we'll say if 92% gives you is 0.19 grams, then what is 100%, which is which is the entire sample of fertilizer. So we'll cross multiply. So in cross multiplying, we will have x is basically equals to 0.19 times 92% divided by oh no, it's the other way around, because you see, you actually multiply it with the 100%. If you cross multiplying, 0.19 is multiplied with 100%, and then you divide by the 92, because you multiply with the x by 92%. Okay, so then we'll put this in a calculator. Let me put it real quick. It really sucks that you can't see this. I wish you could. My calculator, it will make things far easier for you. But anyway, we get 0.21 grams. Now this is of the fertilizer sample. Okay, and that is our final answer. Wow, what a difficult question, but basically we got to the end of it. Okay, let's do the last question now. It says calculate the pH of a 0.5 mole per decimeter sodium hydroxide solution at 25 degrees Celsius. So what do we know about sodium hydroxide? First of all, what we do know is that sodium hydroxide is a base, right? It's not an acid, and pH is based on acid. So we need to solve then a pOH and use the pOH to solve an acid. Okay, so there we go, 7.3. We'll say first of all, we know that the concentration of sodium hydroxide is equals to the concentration of an hydroxide, like that, because it's a strong base, so it's 1:1. So we can then say that since the concentration of sodium hydroxide is 0.5 moles, then the concentration of the hydroxide is also 0.5 moles per decimeter cubed. Right, so now when we come to the equation of pOH, that's going to be equals to minus the log of our hydroxide, right? Okay, and we already know, okay, if we continue here, we already know that minus log, and our OH is 0.5. Put this in a calculator. Put this in a calculator real quick, and we'll get 0.3. Okay, so pOH is 0.3. Now, remember the theory or the principle that pH plus the pOH, when you add them, they equal 14. So pH we don't know, that's what we're trying to solve, but pOH we know is 0.3, that's equals to 14. So then our pH is just equals to 14 minus 0.3, which is 13.7. That's it, nice and quick. That's our pH, very basic. Okay, strong base. Okay, so that's it. If there's anything you didn't understand, I would love to be your tutor. Just contact me on my website, which is www.mvtutors.co.za, or you can WhatsApp me on 076 312 1107. And before you communicate with me, please make sure that you involve your parent or your guardian, because remember, at the end of the day, they are the ones who are paying for the tutoring sessions, so they need to be involved in that whole process. Other than that, thank you so much for listening, and I appreciate you.